In this video, I'm going to discuss binary to decimal conversion. But before I do this, I want to take a look at positional notation, or place values. I have the number 2,168 here. If we look at the place values of the number 2,168, we can see that the place values have the ones place, the tens place, the hundreds place, the thousands place, 10,000, 100,000, and million. These are the place values of the base 10 decimal number system. You can see that we have the number 2 in the 1,000s place, so we have 2 1,000s. We have a 1 in the hundreds place for 100. We have 6 in the tens place for 60. And we have 8 in the ones place for 8. So effectively, we have 2 1,000s, 1 100, 6 tens for 60, and 8 ones for 8. Now, when we're talking about the place values in the decimal number system, we're talking about the powers of 10. You can see that the ones place is the 10 to the 0, the tens place 10 to the 1, the hundreds place 10 to the 2, or 10 times 10, which is 100. The thousands place is the 10 to the 3, or 10 times 10 times 10, and so on and so forth. So you can see that the place values are based on powers of 10. If we look at the number 2,168 then, in long form, we can see that effectively we have 2 1,000s, 1 100, 6 tens, and 8 ones, and 2,000 plus 100 plus 60 plus 8 totals 2,168. This is the type of counting and addition that we learn as children. The decimal system is base 10. It's based on the fact that you have powers of 10, but more importantly, you have 10 characters or 10 numerals in this counting system, from 0 all the way up to 9. So that means that in each place value, you can have anywhere from the number 0 up to the number 9. In other words, if I had the number 9,168, I'd simply replace the 2 here with a 9, and now I have 9 1,000s totaling 9,000 in the 1,000s place. So in any one of these place values, you can have the number 0 all the way up to 9. This is the base 10 decimal number system. If we consider binary and look at it in the same light as decimal, binary is a base 2 number system. There's only 2 characters, or 2 numbers, 0 and 1. So under the place values, we can only have zeros or ones. The place values go from 1, which is 2 to the 0, to 2, 2 to the 1, 4, 2 to the 2, 8, 2 to the 3, or 2 times 2 times 2 is 8. 2 times 2 times 2 times 2 is 16. That's 2 to the 4th power, place value of 16. The 32's place, the 64's place, and the 128's place. Notice that I extended the table to 8 place values. That's because 8 bits is an important grouping of numbers. 8 bits makes a byte in computer processing. So now I have the place values for essentially 8 bits. If I want to write the number 168 in binary, I just have to find the corresponding place values and plug in either a 1 or a 0. So I'll go to the 128's place and ask myself, do I need 128 to reach 168? Yes, I do. So I'll put a 1 there. Now, do I need a 64? I already have a 128. If I add 64, I would get 192 because 128 plus 64 is 192. So the answer is no, so I put a 0. I still have 128 now. Now, do I need a 32? 128 plus 32 is 160, so yes, I could use a 1 here. Now I have 160. Do I need a 16? No, that would make 176, which would go over my target number of 168. I'll put a 0 here. What about an 8? If I add an 8, I'll hit the number perfectly. 128 plus 32 plus 8 is 168. I'll follow this up with zeros in the 4's place, the 2's place, and the 1's place. And 168 in binary equals 101 01000. I now have one 128, I have one 32, and I have one 8. And 128 plus 32 plus 8 equals 168. If we go to the next slide, you can see now that I'm now charged with converting the number 01101101 to decimal. If I want to go the opposite way and convert this binary number to decimal, all I need to do is plug it into the place values. I'll put it in here, 0, 1, 1, 0, 1, 1, 0, 1, and then add it up. I have a 64 and I have a 32. 64 plus 32 is 96. Plus I have an 8, that makes 104. Plus 4 makes 108. Plus 1 makes 109. This number converted to decimal is the number 109. Now let's look at a full IP address in binary. I'll go to my next slide, and you can see in this next slide I now have a 32-bit IP address, 4 octets, or 32 bits total. If I want to convert this binary IP address to decimal, all I need to do is count up each individual octet. Let's start with the first one right here. We can see that 1, 1, 0, 0, 0, 0, 0, 0. 128 plus 64 is 192. Now, the next octet has 10101. Let's do that one. 0, 1, 0, 1, and then all zeros. If we count up the numbers, 128 plus 32 is 160, plus 8 is 168. The next octet is all zeros with a 1 in the last place in the ones place. This is easy. This is the number 1. All zeros and a 1 in the ones place makes the number 1. And then finally, we have a number here. I'll plug it in here into my table. And I have the number 011000101. We can see that 64 plus 32, we've already said, is 96. Plus 4 is 100. Plus 1 is 101. So the conversion of this binary IP address to decimal is 192.168.1.101. This video will cover the process of ANDing as it relates to discovering the network address, the host addresses, and the broadcast address in an IPv4 network. In this example, we'll assume that our IP address is 192.168.1.100/24. Our goal is to answer these questions. What is the subnet mask? We can see that the subnet mask is /24 in slash notation, but what is it in dotted decimal notation? 2, the network address. The network address is the first address in the network. It's a reserved address that cannot be assigned to any host on the network. What is the broadcast address? The broadcast address is the last address in the network and is also a special reserved address that cannot be assigned to a host on the network. And then, since we can't use the network address and the broadcast address, what is the first usable host address on the network? And what is the last usable host address on the network that we can use to assign to hosts, whether they're PCs or printers or servers or access points, whatever? We'll start with question 1. What is the subnet mask? If our IP address is 192.168.1.100/24, this is our subnet mask in slash notation. The first thing we'll need to do is convert this to binary. So I've converted /24 into binary. Notice that /24 denotes that there are 24 ones in the subnet mask, counting from left to right. If we count them up here, we can see that we have 8 ones here in the first octet. Another 8 here makes 16, and then another 8 makes 24. Now I'll need to convert this to decimal. Converted to decimal, the subnet mask is 255.255.255.0. Now how did I do that? Recall that we can take an octet of 8 bits and look at it according to the binary place values. The place values start from 2 to the 0 in the ones place, all the way up to 2 to the 7th power, which is the 128th place. If I have all ones in this 8-bit grouping, then to convert it to decimal is simple as adding 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 equals 255. So each octet with ones in it equals 255. So 255.255.255.0 is our answer. Now let's go to the second question. What is the network address? First off, the network address, to put a simple answer on it, is the first address in the network. So in this case, that would be the address 192.168.1.0. Now you might have assumed correctly that this is the network address. Given a classful Class C IP address like 192.168.1.100 and a classful subnet mask of 255.255.255.0, and you would be correct. The network address is 192.168.1.0. But let's look at it from the perspective of the computer, or for that matter, in the perspective of the router. How does the router know that 192.168.1.100 with this subnet mask has a network address of 1.0? To do this, we take the IP address and the subnet mask and we convert them first to binary. So you can see in this table, I have the IP address 192.168.1.100 here on the upper row, converted to binary. The subnet mask 255.255.255.0 is converted to binary on the lower row. The router and your computer can calculate the network address by combining the IP address and the subnet mask. This process is called ANDing. ANDing, or logical ANDing, is a logical conjunction where we need to figure out whether the statement A and B is true or false given a value for A and a value for B. So logical ANDing really involves a truth table. If A is true and B is true, then the truth of A and B, with the necessary condition being the conjunction and, is also true. Since A is true and B is true, then A and B, the requirement and, meaning both of them, is also true. But if A is true and B is false, then the conjunction of A and B is false. And if A is false and B is true, then the requirement of and for both of them is false. And if A is false and B is false, then the requirement that they both be true is not met, and A and B is false. We then convert the true and false to the Boolean values for true and false, 1 and 0. And we have a Boolean truth table. The router and the computer use this logical ANDing with 1s standing for true and 0s standing for false to do a logical ANDing operation between the IP address and the subnet mask. So you can see here in the example, the IP address has a 1-bit, the subnet mask has a 1-bit, and the conjunction or the ANDing operation between them results in a 1, or a true and a true makes a true. And so then a 1 and a 1 makes a 1, and a false and a true, or a 0 and a 1 results in a 0. And so now you have all zeros here. And then in the next octet, you have a 1 and a 1 equals a 1. And a 0 and a 1, or false and a true, results in a false. And a true and a true makes a true. And a false and a true makes a false. And so on and so forth. Notice in the final octet, the subnet mask is all zeros. And the result is all zeros. And the resulting network address is 192.168.1.0. This process of ANDing is crucial for how the routers and computers are able to determine the network based upon the IP address and subnet mask. So now we know that the network address is the first address in the network. We also know a little bit more about how the network address is actually determined by the computer or the router. And we can go to question number 3, what is the broadcast address? If the network address is the first address in the network, the broadcast address is the last address in the network. In this case, the broadcast address would be 192.168.1.255. Let's plug the 192.168.1.255 broadcast address into our table and do the ANDing operation just to prove that it's still within the one network. If we go up here to our table, I can replace this 100 right here in this fourth octet with 255. So now you can see that the IP address is 192.168.1.255. If we do an ANDing operation between the broadcast address here and the subnet mask, you'll see that it generates the same result. Notice a true and a true makes a true and a true makes a true, false and a true a false, all the way over. And when we get to the last octet, a true and a false is a false, a true and a false is a false, and you can see that the ending result of network address is still 192.168.1.0. Now if we go to the next higher address and jump up from 1.255 to 2.0, let's say, we'll change it here, put a 1 here, and a 0 here, so now that's a 2, and we change this to all zeros. You can see that we're going to get a different result. Notice the ANDing operation. A false and a true is a false, 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 but when we get here, a true and a true is a true, and a false and a true is a false, and now the network address is the 2 network, 2.0. So you can see how important ANDing is to defining just where the networks lie. This brings us to the last question. What are the first usable and last usable host addresses in the network. The first usable host address in the network is the first address after the network address. So in this case, the network address is 0, so the first usable host address would be 1. The last usable host address is the address prior to the broadcast address. So in this case, the broadcast address is 255, so the last usable host address would be 254. So now we've answered all 5 questions: the subnet mask, the network address, the broadcast address, and the first and last usable host addresses, given an IP address of 192.168.1.100/24 with a 24-bit subnet mask. First of all, when we're talking about classful IP addressing in networks, we're talking about Class C, Class B, and Class A addresses. Now, what makes a Class C, Class B, and Class A address and network? Two things: the IP address and the subnet mask. In order to have a Class C IP address or Class C network, you need the IP address first octet to be a number between 192 and 223. You also need the subnet mask to be 255.255.255.0. As long as you have these two requirements, you would have a Class C IP address and Class C network. To have a Class B IP address and network, you'd need the IP address, the number in the first octet, to be a number between 128 and 191, and the subnet mask would need to be 255.255.0.0. For a Class A IP address and network, the first octet address number would need to be a number between 0 and 127, and the subnet mask 255.0.0.0. Now you might ask yourself, why these specific numbers? 0 to 127 for Class A, 128 to 191 for Class B, and 192 to 223 for Class C. It all has to do with the fact that the router and the computers see the IP addresses and the subnet masks in binary, not in dotted decimal notation. This is just the decimal representation of what the computer sees in binary. So if we look at it in binary and we take a look and convert the first octet in the IP address to binary, we see that in order to have a number between 192 and 223, the first three digits in binary, counting from left to right, need to be 1, 1, and 0. If the first three digits are 1, 1, 0, the number has to be between 192 and 223. And for Class B, if the number starts with a 1, 0, then the resulting number will be constrained to 128 to 191. And in Class A, as long as in binary the number begins with a 0, the number in decimal representation can only be 0 to 127. So the restrictions on the numbers 0 to 127, 128 to 191, and 192 to 223 are due to how the address functions in binary.